Okay, Unit 1. Now, of course, copy all of this into your notebook, and you can use the spacebar to stop and start as needed. Unit 1 will consist of IB's Topic 2, Atomic Structure, and IB Topic 3, Periodicity. Much of this you've already had. So note, for the material that was covered in first year chemistry, you will see review, so written like that, kind of in script and red, at the top of each of these notes, each page of these notes. For that material, I strongly suggest finding it in your chemistry notebook from last year. Hopefully you took good notes. Now that doesn't mean to say don't copy these notes down, but just a reminder that we've gone over much of this stuff before. And as I've already told you, these two sites that you find on our Canvas page are just amazing tutorials. So please remember that. Go to the tutorial button on the home page, and anytime you find something that doesn't quite click or you want to review, please take a look at these two. They're really, I cannot, I have no investment in the company. They aren't companies, but they're just terrific. And also, when you see this little triangle at the beginning of a page with some heading, that means that we're starting a new topic. So in your notes, do something to indicate a new topic is being started. It'll help you out. And also, by the way, a lot of you, when you take notes, you just cram everything together. It's really hard to see where one thing stops and one thing starts. Please space out your work. Quite often you need to add stuff in, or maybe there was a mistake and you need to make a correction. So, you should have plenty of paper. If not, I'll help you out there. But spread your work out. Leave margins, spacing between topics. Just a suggestion there. Okay, 2.1, the nuclear chemistry. Now this number system, 2.1, 2.2 is electron configurations. That's straight from IB, so following IB's lead. And this is an animation of the atom as we know it. Of course, the nucleus is blown up. This is not to scale. If this was the size of the atom, you would not be able to see the nucleus. It's way too small. Okay, subatomic particles, the constituents of an atom. Okay, now we're going to list what the particle is: simple, location, relative charge, relative mass, and actual mass. Now the terms relative just means one thing compared to another. So for example, if you were 16 years old and I was 48, we could say your age is 1, my age would be 3, without any units associated with that, like minutes or hours or years. So relative, just one compared to another, as you'll see. The proton is given the symbol lowercase p, and it's found inside the nucleus. It has a relative charge of +1, a relative mass of almost 1, and the actual mass of 1.673 times 10 to the negative 24 grams. The neutron, symbol lowercase n, it's also found inside the nucleus. Relative charge of 0, and that's where the name comes from. Neutron, that's neutral, has no charge. And the relative mass is almost 1 as well, but it's ever so slightly more massive than a proton. It's 1.675 times 10 to the negative 24. Collectively, the proton and neutron are referred to as nucleons, so it's a term you'll hear a lot. The electron, symbol lowercase e with a negative sign on it. Now, sometimes you'll see the P for proton with a little positive sign, and the N for neutron with a little 0. IB doesn't use that. I don't use that, but you'll see that now and then, and that's all it means. Nothing different. The electron is found far outside the nucleus. Relative charge is -1. What we say is that the proton and electrons, their charges are equal in magnitude but opposite in sign. The mass, very small. You would need to have about 2,000 electrons to have the same mass of a proton or a neutron. And its actual mass is 9.11 times 10 to the negative 28. Symbolic notation. Chemists use a specific notation to indicate the number of subatomic particles. So for example, we can see this represents bromine with various numbers of electrons, protons, and neutrons. So we'll dissect that in a minute. When you see a number written above to the right or to the left, we refer to those as superscripts, and below as subscripts. One way to remember that, Supergirl, Superboy, Superman, Superwoman, flies high, goes up, so super, and submarines go down, subscript. Okay, so let's take a look at what each one of these numbers mean. Okay, now the symbol itself, of course, we just get that from the periodic table, whatever element we're referring to. The Z is the atomic number, which is the number of protons. That's what defines an element. The Z comes from Zahl, German for number. Mass number A, it's the number of protons plus the number of neutrons, or we could say it's the total number of nucleons. Now, if you wanted to know the number of neutrons, you'd have to do a little subtraction of the atomic number subtracted from the mass number. So A is the total number of protons and neutrons, so if we subtract the atomic number, which is the number of protons, we would get the number of neutrons. The A comes from Attekovich, German for atomic weight. Now, elements may have a charge, a positive charge, may have a negative charge, or no charge at all. And we can determine that by taking the number of protons, remember are positively charged, and subtract from that the number of electrons. So if we have the same number of electrons and protons, there would be no charge. If we want to know the number of electrons, we would take the atomic number of protons, and subtract the charge. And we'll practice this in a few minutes. And by the way, the A and the Z, don't worry about that. That's just I pointed that out. IB likes to use that, and you'll see it now and then. You know, the symbols A and Z. All right, let's look at determining the number of protons, neutrons, and electrons given a symbol. So here, 2 is the atomic number, so that's the number of protons. So we can read that straight off. The number of neutrons we can determine from the mass number. We take the mass number, subtract the atomic number, and that would give us 2 neutrons. The number of electrons, you can already tell that we have 2 because there's no charge, so we must have the same number of protons as electrons. Or we could say the atomic number minus the charge, 2 minus 0, gives us 2. Let's do another one. Now remember, you can press the space bar anytime you want to try these things yourself without watching me walk you through it. Now magnesium has an atomic number of 12, mass number of 24, and a positive 2 charge. Now make sure you always write the sign after the number. It's a convention that's used to not confuse the ionic charge with what's called the oxidation state, and that'll make more sense to you later on in the course. But always write the sign after the number for the ionic charge. So the number of protons, of course, is just the atomic number, 12. The number of neutrons would be the mass number minus the atomic number, again 12. Now we can do the little subtraction to determine the number of electrons, but the easier way to do that is just remember that electrons are a negative 1 charge, protons are positive 1 charge. So since it has a positive 2, it must mean that you have 2 more protons than electrons. So, or we can do the subtraction, atomic number minus charge. Either case, you get 10. Okay, now let's go the other direction. You would need a periodic table for this. So what element has 17 protons? It would be the element that has the atomic number of 17, and that would be chlorine. So atomic number, we need to add together 17 plus 18 protons plus neutrons to give us the mass number. And we can see that we have 1 more electron than protons, so it would have a negative 1 charge. Or we could go 17 minus 18 to give us a negative 1. On the periodic table, the element that's atomic number 82 is lead. Adding together 82 plus 128 gives us the mass number of 210. And we can see we have 4 more protons than electrons, so it has a positive 4 charge, or 82 minus 78. Okay, the elements, chemical elements. An element is a pure substance consisting of atoms that have the same number of protons. For example, all hydrogen atoms have 1 proton, all helium 2 protons, lithium 3 protons, etc. That's what defines the element. If you were to take lithium and remove a proton, it would no longer be lithium, it would be helium. There are 92 chemical elements that occur naturally, hydrogen to uranium. Elements beyond uranium are called the transuranium elements and are synthetic and will undergo radioactive decay. Synthetic means that they are artificially made. They're made in the lab. Okay, so let's take another look at this periodic table here. It's just blown up. Remember that the inner transition elements, the 2 rows in the bottom here, rightfully belong right here. They're pulled out just to make the periodic table more compact. But if we put them where they belong in what's called the expanded periodic table, you have a better sense that the synthetic elements, or the transuranium elements, are all in a row. Okay, so these were just verified a few years ago. The next, which are certainly coming, will come down here. Periodic table goes, the periods are 1 through 7. Soon we'll have a period 8 with these synthetic elements being added. Atoms are the smallest unit of an element and contain the same number of electrons and protons. So for example, carbon, that has atomic number 6, so it's 6 protons, the atom has also 6 electrons. There's no charge on it. If we gain or lose electrons, they become ions, or carbon would become an ion. Ions are atoms that have lost or gained electrons. Positive ions are cations. Electrons have been lost. So if we take our carbon here, remove electrons, in this case 4 electrons have been removed, it'll have a positive 4 charge. Negative ions are called anions, and here electrons have been added. So if we add electrons to carbon, in this case adding 4 electrons, it'll have a negative 4 charge. So it now has 10 electrons. So, and if we say something it's an atom, it has no charge. If it's an ion, it'll either be a cation with a positive charge or an anion with a negative charge. And by the way, carbon is unique in its ability to be either a positive or negative ion. A few other elements can do that, but mostly all nonmetals are negative, become negative ions, anions, and all metals become cations. Isotopes are atoms of the same element with different numbers of neutrons. So we're going to look at potassium as an example. And what you're looking at here is a blow-up of the nucleus of 3 different isotopes of potassium. Now they're all potassium because they have 19 protons. So 19 protons, 19 protons, 19 protons. And you can see the little positive sign on the P, like I was telling you earlier, and the 0 on the N. There's nothing special about that. It's just another way of indicating protons and neutrons. A little bit more explicit, I guess. All right, now, how do we represent these 3 isotopes? If we talk about potassium, which one are we talking about? Well, there's 3 different ways of doing that. We can either use the symbolic notation that we've already discussed, but a simpler, more common way of doing it is to write the name of the element and with a hyphen and the mass number. So potassium 39 is exactly the same as this. Now remember, the 39 is not the number of neutrons, and that's a really common mistake, so don't fall into that. It's the mass number, which is the total number of protons and neutrons. So we add together 19 protons and 20 neutrons, we get the mass number of 39. So potassium 39, that's the mass number. An even simpler way of writing it is the symbol for the element hyphen mass number, so K39. So to distinguish between these 3 isotopes, all we need to do is to change the mass number. Here the mass number would be 40, 19 plus 21, and here 19 plus 22 would be 41. Okay, now our next topic that we'll get to next time is calculating atomic mass. So when we look, if we had a sample of potassium in nature, we would find we would have a certain amount of that potassium would be one isotope, a certain amount would be another, a certain amount would be another. So when you look on the periodic table and find the atomic mass for potassium, which is 39.10, where does that number come from? So that is a weighted average calculation you might remember from last year, and that will be our topic next time. But for now, that is the end of today's notes.